Hello, this is Matt Roscoe here at the University of Montana, and this is the second half of the lecture on Chapter 7.7, Comparisons of Improper Integrals for our Calc 2 course this fall. Hopefully in the first part of this um, lecture on Wednesday, we were able to talk a little bit about motivation and, knowing about convergence of this particular improper integral will tell us something about the conversion of this integral because the argument in the integrand here is always going to be, I guess, greater than the argument here. So if this one lies underneath that one and this one converges, then that one has to converge too. And that's what we said in words here. And you can play the game backwards for divergence. If something underneath the function diverges, then the larger of the two has to diverge as well. So those were kind of the two games we talked about in the chapter, making these comparisons. And then we took a look at a few problems in class. I think we did this one and this one. And here's where we probably left off. We'll take a look at this one today. So let's think about this integral first. We have 1 over an exponential function plus a constant. We know those exponential functions go to infinity fairly quickly, so 1 over that we would assume is going to 0 very quickly. And the speed at which it's going to 0 is even heightened by a multiple of 5 there. So it seems to me just intuitively that this one should probably converge. But let's go to Desmos and see if that's true. I'll pull in my Desmos picture here. I'm using my improper integral explorer, which you have a link to in this week's activity, or excuse me, with this week's lecture there. You should see it on Moodle. So I just put in the function and I'm integrating the function from 1 to infinity, but it turns out that really all I have to do is go from 1 to 3 to get a good sense of what's going on. I can see that, if I start back here at 1 and start accumulating area, it's growing, 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 but then things flatten out pretty quickly. And we can see that we're, 1, 2, 3, 4, 5 decimals, 6 decimals not changing. It's getting pretty close to, it seems like a specific value. If I bumped it out, let's say to 5, and saw if it changed any more there, now we're seeing 7 or 8 decimal places of convergence. It sure appears like we're approaching a finite number, so our guess here would be that this is definitely convergent. But how do we, prove it mathematically beyond a shadow of doubt? We're relying on technology to show us that it seems like it's true. Let's try to prove it mathematically. So I'll switch over to my Elmo Cam and we'll take a look at this. And see if we can get a sense. Okay. So what are we trying to do? We're trying to find the integral from 1 to infinity of 1 over e to the 5t plus 2 dt. Actually, we're not trying to find it. We're trying to just determine whether or not this converges or if it diverges. And that's the question we're trying to answer. Simple yes, no question. And we think Desmos tells us that this thing probably converges. In the game that we usually play is we try to trap this for convergent functions. We try to trap this function under another function whose convergence can be analyzed more readily, and then make the argument that if the upper function converges, then the lower function, which is inside of the upper function's area, should also converge. So let's think about what function we'd like to trap this underneath. And to me, it seems like the function that makes the best sense would be 1 over e to the 5t. I think I could compute that function's improper integral. It doesn't have this constant kind of in the way. If we could get a handle on that one, then it might help us get a handle on this one. So the big question, I guess, is 1 over e to the 5t plus 2, how does that relate to 1 over e to the 5t? And it's pretty easy to see that this one has a larger denominator than that one whenever t is greater than 0, and it certainly is in the limits of integration here. So if it has a larger denominator, it's going to be a smaller number in values. So in other words, this is the inequality that we would have, for any t in our domain. So for t greater than 1, certainly this works. So that means that if I evaluate this integral, the integral from 1 to infinity for this function, and it converges, then since this function is underneath it always across, the limits of integration, then this one has to converge because it's some subset of this one's area. So that's the idea of the game that we're playing. Let's go ahead and take a look at how it's going to work. So we're going to use this one and evaluate its convergence, and if it does converge, then it'll tell us that this one converges because it's underneath. Okay, so let's see, this is the limit as b goes to infinity of the integral from 1 to b of 1 over e to the 5t dt. Well, that works out all right, but the 1 over thing doesn't seem like it's going to help us much, so let's go ahead and write that as a negative 5t. So we'll call this the limit as b goes to infinity of 1 to b e to the negative 5t dt. And now we can use simple w substitution. We'll let w be equal to negative 5t. We'll let dw equal to negative 5 dt, which means that negative 1/5 dw is equal to dt. So we'll use that substitution to get to limit from as b goes to infinity. Now let's just think about, let's change the limits of integration using what we know to be w. So these are t's, right? So if we plug those into this relationship for t, they'll tell us what w's to use. So 1 into negative 5 times 1 would be negative 5, and b into this would be negative 5b. And we get e to the w and times negative 1/5 dw. So what does that get us? Let's see. So cleaning up a bit, we'll do the limit as b goes to infinity from negative 5 to negative 5b. We'll pull the negative 1/5 out in front, and it'll be just e to the w dw, which is nice because, of course, the antiderivative of e to the w is just e to the w. That gives us the limit as b goes to infinity of negative 1/5 e to the w evaluated from negative 5 to negative 5b. And that's easily evaluated. Let's go ahead and do that. We'll have the limit as b goes to infinity of, let's see, negative 1/5. I'm putting negative 5b in for w, so it's e to the negative, sorry, that should be a 5b. Okay, and then let's see, I'm going to subtract away from the limit at the other end, so it'll be negative 1/5 e to the negative 5. And now I can see that, well, this will become a plus, and I can take the limit here. So we'll have the limit as b goes to infinity of negative 1/5 e to the negative 5b plus 1/5 e to the negative 5. And the question now becomes, well, what is this guy doing as b goes to infinity? So we're going to take the limit on this piece, apply the limit to that piece. And of course, this is a negative exponential function, and those things go towards 0 as b goes to infinity. So this piece goes towards 0, and we have negative 1/5 times something going to 0, so that's going to 0. So this whole thing is going to 0, and we're left with just this piece. So So what we've shown, I guess, is that we have to kind of go back and look at what you've done here, but is that the limit from 1 to infinity of 1 over e to the 5t dt is equal to a finite value. It's 1 over 5e to the 5th. So it converges. But remember, that's not the one that we we wanted to solve, and so we can make this comparison, right? And the comparison is this, and that's that the integral from 1 to infinity of 1 over e to the 5t plus 2, the one we were after, right, dt, that's always going to be less than, right, the integral from 1 to infinity of 1 over e to the 5t dt. The reason that's less than that is because this function is always greater than that function across the limits of integration. That's something we resolve. And that's all. This one is equal to 5e to the 5th. Oops, did I get something wrong here? Oh, I'm okay. Sorry, that's 1 over 5e to the 5th. I have an error in my notes. Okay, so since this one's finite, and this one is less than that one always, we can say the integral from 1 to infinity of 1 over e to the 5t plus 2 dt converges. And here's kind of an interesting fact. It's going to converge, but it's got to converge to something less than this, right? So it turns out that it's got to be smaller than 1 over 5e to the 5th, which is, it gives you an upper bound, I guess. And who knows how much less, this one is. I guess it's 2 units in the denominator. Well, yeah, hard to sort of scale that. But we know for certain that it converges because this function's underneath this function across the limits of integration, and this function converges. I hope that makes sense. So by now you're probably thinking, well, I've seen some patterns here. It seems like there are certain types of functions that seem to converge, and that's the next piece in this chapter. Your textbook gives you some important results that you can use for comparisons and you can rely on. I'd encourage you to have these on your cheat sheet for the test. But they should make sense to you. This one, from 1 to infinity, the integral of 1 over x to the p dx converges anytime p is greater than 1. In other words, if we're taking a power of p, that's greater than 1, then that thing is going to 0 fast enough that we're going to get convergence. And when the power of p is less than or equal to 1, then it turns out that it diverges. And we've seen several examples of that in our study. For example, one of the first things we looked at was 1 over the square root of x. And if we think about that one, that was the first divergent example I showed you in 7.6. And if you think about the power there, the power of the square root is 1/2, and certainly that's the case here, that when p is less than 1, one example being p equal to 1/2, we get a divergent improper integral from 1 to infinity. The next rule has to do with, well, what happens to this same exact function between 0 and 1? So notice the difference in the limits of integration, and it's just the it's the opposite of what happens between 1 and infinity. So between 0 and 1, it converges if p is less than 1, and it diverges if p is equal to or greater than 1. So again, it's just a difference of the limits of integration here from 0 to 1. So a couple important results, and then another one that has to do with the problem that we just saw, and that is the exponential function. When we have an exponential decay function, that's e to the negative ax, when a is, greater than 0 here, meaning that we have a true decay function, you don't have a negative times a negative, then all those decay functions converge. And notice the limits on integration here are from 1 to infinity, so no sort of hiccup at 1, like 1 over x to the p. This works for anything from 0 to infinity. And of course, if it converges for 0 to infinity, it would converge, to 1 to infinity as well. And of course, they diverge when a is less than or equal to 0. If they're equal to 0, you get a constant function here, which, sums to infinity. And if it's less than 0, then instead of exponential decay, you get exponential growth, right? Because a negative times a negative would make a positive in the exponent. And of course, exponential growth will never converge. It explodes to infinity very fast. So I guess those are important results you can rely on, and our last two examples rely on those two results. So let's take a look there. So let's decide whether or not the following integral diverges or converges. So let's just take a second to look at this on Desmos and peek at what it looks like. Okay, here it comes. So here's what that function looks like. And remember, we're going from 1 to infinity, and I can see that as I sum it to 20, things are starting to sort of, they're still growing pretty good. If I sum it to 40, let's do that next. Still growing pretty good. Let's say if I round it out to 1,000, you can see that, oops, let me pause here. Okay, so to 100, we're at 54. And if I ran this out to 1,000, yeah, it's definitely growing still more. So to me, what it looks like is things are diverging, because I can make this number just as large as I want it, depending on how big I make this number. Of course, it's not growing very rapidly, but it's still growing and doesn't appear to be approaching any definite value. And if I march it way back, I can definitely see that it counts pretty good for me. Doesn't seem to be flattening out. So the first thing you might notice is that the function that we have is built of sort of three functions: a sinusoidal function, a constant function, and then a 1 over square root function. So it might be informative for us to think of 1 over square root first. And so I've put that in there, and I can see there's 1 over square root of x. And we know from the rule that 1 over x to the p diverges when p is less than 1 and the limits of integration are from 0 to infinity, which is the case we have here. In other words, the 1 over square root function just doesn't go to 0 quick enough in order for this thing to converge. But what's kind of troubling is that there's this space above. And so, the space above has to do with what's going on top here. So the sine function, of course, oscillates between 1 and -1. So on top, the most we're going to have is 1 plus 3 or 4. So if I put that, then, those are all the tops, right? And the least amount that we're going to have, I'm going to just copy this and hit enter. Oops, turn that on. And put this in. So the least we would have would be -1 plus 3, so that would be just 2 on top, and those are the two, I guess, upper and lower bounds on sort of the envelope of integration here, right? But what's kind of, I guess, a moot point is that if we just show that 1 over the square root of x, which is certainly less than the value of the function. We can see that it's always less than, because the maximum the function takes is 4 over the square root of x, and the minimum the function takes is 2 over the square root of x. And this number will always be smaller because the numerator is smaller than either 4 or 2, or any number in between them. So we can just simply think about this number. If that particular area diverges, then we're good to go. And So let's just sort of come down here and do this again with 1 over square root of x, and throw that in there as a red graph with red shading. So in other words, if we can show that that red shading, which is always going to be less than the blue shading, diverges, then we know for certain that the blue shading has to diverge because it includes the red shading, which diverges. I hope that makes sense to people. But that's the idea here. For proving divergence, you have to pick something that's less than it, less than the value of the function, and which you can show diverges. And if that's the case, then adding something to a divergent area will still be a divergent area. Okay, so let's go ahead and switch this over to our ElmoCam and think about how we would explain that to the reader. So we're trying to answer the question. Oh, I better make this bigger. So we're trying to answer this question, does the integral from 1 to infinity of sine x plus 3 all over the square root of x dx, does it converge or diverge? And we think the answer is diverge. And so, the game is just the opposite of what we just did the last time on the last example. It's to find a function that's less than this function always, and show that it diverges. And if it diverges, then adding more to it will also diverge. So, what I would say is notice that 1 over the square root of x is always going to be less than sine x plus 3 all over the square root of x. You might want to explain this. It's because this thing is always going to be between, I guess, -1 plus, well, maybe I'll just do this. I know this because this function sine x plus 3 all over the square root of x is in between these two functions. Let's see if in the maximum value it takes on sine x is equal to 1, and we get 4 over the square root of x. And the minimum value that this function takes on, I guess, or the smallest sort of envelope that we saw in Desmos would be when this is -1, so we'll get 2 over the square root of x. So since this is between 2 and 4, square root of x, and 1 over square root of x is certainly less than than the 2 and 4 case, I can say something like this. This is strictly less than 1 over square root of x. I hope that makes sense to people. This thing's oscillating between these two extremes, and this function is definitely less than this. And we know this function diverges from the rule. So, but the integral from 1 to infinity of 1 over x to the 1/2 dx diverges. So the integral from 1 to infinity of sine x plus 3 all over the square root of x dx does also. So I hope this kind of helps you sort of think about how the game gets a little easier once we know these three big results about 1 over x to the p and e to the negative ax. All we have to do is if we can relate one of these integrals to one of these 1 over x to the p's or e to the ax, then we can rely on that instead of having to carry out the actual, I guess, integration and with the limit. Okay, I hope that was informative. So we know for sure that sine x plus 3 diverges. Sorry, sine x plus 3 over the square root of x diverges on the interval from 1 to infinity. I should be a little bit careful about how I say things. Let's do one more. Okay, let's take a look at this one. We're trying to decide whether or not the following integral diverges or converges, where the limits on integration are 0 to infinity. It's 1 over e to the z plus 2 raised to the z dz. And so what can we say about this? Right away the intuition for me is this thing's got to converge. I mean, e to the z is in the denominator means that we have a function e to the negative z, which we know converges based on our one of the previous slides. Just so long as that exponent on e is negative, we have negative exponential decay, and those negative decay curves always converge if we're integrating from 0 to infinity. Now the 2 to the z we know very little about, and I mean thinking about trying to integrate this function is even more sort of problematic. I don't know where we would really start. So we're left with sort of trying to trap this function underneath a greater valued function, and showing that that greater valued function converges, and if that greater valued function converges, then this one, the lesser valued function, should also converge. So let's switch over and try this one first mathematically, and then we'll go to Desmos to confirm. So I'll switch over to my ElmoCam, and so we're trying to find out integral from 0 to infinity 1 over e to the z plus 2 to the z dz. Does it converge or diverge? And we think, our guess is that it converges. So what we really need to do is we need to relate this function to one that we know that does converge, that's greater in value across these limits of integration. And the right one to do, of course, is to compare this function 1 over e to the z plus 2 to the z to this function 1 over e to the z, which is of course equal to e to the negative z, which we know these ones converge in these limits of integration based on the information given in the previous slides. And it's pretty easy to see that this one's got to be smaller than this one because it's got a larger denominator, right? I mean, 2 to the z, as long as z is positive, and of course it is, you're going to be adding something to that term, so we get a larger denominator, smaller number. This is always less than. And since we know that the integral from 0 to infinity e to the negative z dz converges, then so must the integral from 0 to infinity 1 over e to the z plus 2 to the z dz. And again, this is this idea, if you can find one that's above it, right, that converges, then the one that's below must also converge. Let's take a quick look to see if Desmos also confirms our mathematics. So I'll pull down my Desmos here. Okay, so here's a picture of the integral we're trying to obtain. So it's 1 over e to the x plus 2 to the x, integrated from, I guess we should, limits of integration were 0 to infinity. And we can see that this number up here is stuck solid here until I get back under 100. I can't remember here. So somewhere in the 20s it starts to converge. But it doesn't take it. So really we don't need much more than 20 here. And step it by ones and see what happened. So you can see kind of the convergence getting close there as we get close to 20. It seems to be somewhere in the neighborhood of 0.573. Of course, we don't know what the exact number is here, but we get pretty darn close to it, at least within the limits of accuracy of Desmos. If we run it out to 40, boy, it converges by about 30 for these 10, I think it's 10 decimal digits of accuracy. So it seems like that thing's going to zero very fast. No surprise, right? Because e to the x and 2 to the x are both exponential functions, and the true exponential and a base 2 power function. So they're blowing up to infinity very quickly, so the 1 over them is going to zero very quickly. So no surprise. But what we effectively did to prove that this was true is we related it to this function, just 1 over e to the x. In other words, we thought, oh, just get rid of the 2 to the x, because this one is going to always be greater, right? And it also has a convergent improper integral from 0 to infinity. In fact, it turns out that it converges to 1, and so the red area, the one that's greater, converges to 1. So that means the blue area, the one that's the function that's less than, is going to converge to some value less than 1, and indeed it does. So close-up picture of sort of what's happening here. If I adjust the limits of integration, we can see that no matter where we're at in here, the red area is always going to be greater than the blue area, and as the red area has been shown to be convergent, the blue area has to be convergent as well, because it's a part of the red area. It's a subset or a piece of the red area. All right, that's really all I have for you today. I hope that this gives you some new tools to think about making comparisons. Remember that the only thing we're after here is to decide whether or not something converges or diverges, and that can be more easily done by making comparisons to easier arguments in the integrand. Okay, I look forward to seeing you guys all on Monday when we'll do some reviewing, get ready for our test on Tuesday. Wish you luck on the homework on this section, and bring me your questions on Monday if you have them. All right, take care.